All right, thank you so much for joining us today. So, we've looked at linear differential equation, we've looked at separable differential equation, we've talked about homogeneous differential equation, we looked at exact differential equation. Now, the big question comes in, what if the last method that we just discussed is not exact? What do we need to do? Then we have a way of doing it. A way of doing it, we need to talk about integrating factor. You remember we talked about integrating factor when we started linear differential equation, right? Yeah. So if the equation is not exact, then we can find integrating factor that will make sure that now the equation becomes what? Exact. So that's what we just need to look at. So the example here, we can see that, let's look at this one here. We can see that if I have this question like this is the same as x squared y minus y to the power 4 dx plus 2xy cubed minus s cubed dy is equal to 0. So my p of xy is equal to x squared y minus 4 or y to the power 4. This implies that p of y, I mean differentiating with respect to y, I'm going to have x squared minus 4y cubed. But what is for the q? Now with the q, I'm going to have q of xy is equal to 2xy cubed minus x cubed. But q of x is equal to 2y cubed minus 3x squared. And we see that this is not the same as that. Good. So that's where what's integrating factor comes in. So if this is not the same as this, then we cannot use the method of exact differential equation to solve unless we make it exact before we can use the exact differential equation. So let's talk about integrating factor. So the thing is, now we want to find integrating factor such that now when I multiply this equation by the integrating factor, now the resulting equation become exact. What do I mean? Now we know that this is how we need to form the exact differential equation, but we saw that solving this one does not give us the exactness. So what do we need to do? We need to find integrating factor. So when I find the integrating factor, I'm going to multiply through this equation by the integrating factor. So I'm going to have something like this: mu of xy, q of xy dx plus mu of xy, q of xy dy is equal to 0. And as soon as I do something like this, if this is the integrating factor of this differential equation, then this new equation now becomes exact differential equation, right? And from here now we will see that we will pick our new function. So you see that the other one we pick p of x, y, and we are going to look for partial of p of x with respect to y, and then q of x, y, and then we are going to look for partial of q with respect to x. But in our new function, you will see that now we are going to pick mu of p of x, y, and now we are going to look for partial of mu of p x, y with respect to y, and then q of xy with the mu, and this is going to be mu q with respect to x. So you see that the only difference here is now that when the equation is exact without finding integrating factor, we just have the p, q. But when the equation is not exact and we find the integrating factor, now we have the integrating factor associated with the p, same here, same here, and same here. Right. So now let's take one example, and we want to show that this is indeed the integrating factor of this. So when we say this is an integrating factor of this, what we mean is now when I multiply this one to this, now the equation will become exact. Now for me to show you, first I will just solve this one. Oh, we've already solved this. I think this one was what we just solved here, and we saw that yes, indeed, this is not exact differential equation. So what we just need to do is we need to multiply through by the integrating factor. So let's do that and see if it is true. So what we need to do is, now we are going to multiply this equation by that. So we are going to have mu x y, x squared y minus y to the power 4, or let me just simplify this one first. So x squared y minus y to the power 4 plus 2xy cubed minus x cubed y, no, dy over the x. Let's get the standard form, x squared y minus y to the power 4 dx plus 2xy cubed minus s cubed dy is equal to 0. So now this is what you are getting now. Now we know that this one is not exact because we've done it already. So we just want to see if this is the integrating factor of this differential equation. So for us to do that, we need to multiply this equation by the integrating factor. So let's do that. We are going to have x minus 2, y minus 2, x squared y minus y to the power 4 dx plus x minus 2, y minus 2, 2xy cubed minus x cubed dy is equal to 0. Good. So now remember, if the function is not exact and we multiply through by the integrating factor, now we don't pick p of x, y, we pick mu of what? So the standard form for integrating factor now is mu p of x y dx plus mu k of x y dy is equal to 0. So that's what we need to know with finding integrating factor. So now we have mu p of x y, which is equal to x to the power minus 2 minus y to the power minus 2 x squared y minus y to the power 4. That is our new p. Then mu of k of x now will be the coefficient of dy, which is minus 2y minus 2 2xy cubed minus s cubed. But we can simplify this by multiplying through by this so that the differentiation becomes easy. So when I multiply through, now x times this will be 1, right? Because if I have x minus 2 times x2, this is the same as x to the power minus 2 plus 2, and this is x to the power 0, which is 1. So that one will be just 1. And then when I multiply this one by this one will just give me y to the power minus 1. Then minus 2 and y squared. So when I multiply, that's what I'm going to get, because 4 minus 2 will be 2. And then I'll have this one with this one. Good. Now, what about this one too? This one too is going to give us 2x to the power minus 1 y minus x y to the power minus 2. So multiply this one by this, and this one will be left with minus 2 and 1 will be minus 1. Minus 2 and 3 will be 1. Multiply this, minus 2 and 3 will be 1, and the minus 2 will be here. So now what we need is, we need to find partial of mu p with respect to y. So let's differentiate this with respect to y and see what we are going to get. So this is to the power minus 1, so I'm going to have minus y to the power minus 2, differentiation. So drop the minus 1, subtract minus 1. Then minus, I'm differentiating with respect to y, so I need to just maintain this and differentiate this. So I'm going to have 2x to the power minus 2y. So this is the differentiation that I'm going to get for that one. Then go with mu k, but this one with respect to x. Now let's differentiate this with respect to x. Now do the same thing for this. The minus 1 drops down, so I'm going to have minus 2x subtract 1, so minus 2y. Then minus, differentiate this with respect to x, so the x just go away, so I'm just going to have, and we see that this is the same as that, because this the same as this, and this is also the same as that. So we are saying that since this of p, mu of p of y is the same as mu of q of x, since this is the same, then mu of this is the integrating factor of the differential equation. So basically that is how it is. But the question is, it's not always the case they are going to give you the integrating factor. So for example, now that we've multiplied through the equation and you've seen that it is what? It is exact, then now we use this for our big F of x and this for our big F of y. Then we go through the process that we went through, the same at the exact differential equation. So basically that's all. When we make the function exact, the same process for the exact differential equation is what we go through. But the question is, what if they've not given us the integrating factor? Then what do we need to do? Then we need to find our own integrating factor. So here we are going to learn how to find integrating factor and then use it to solve the differential equation. So what we just need to do is, we have two forms of the integrating factor. The rest of the integrating factor, we can learn it when we are dealing with ODE in level 400. So what are we doing here? This guy here is one form. And when we do this, this should be a function of only x. Like when I pick partial of y, partial of x divided by q. So this one is easy to memorize or remember. This is like partial of y minus partial of q. Then you pick the last term and you use it to divide. So divide by q. And then when we're able to do this and get it in terms of x only, then the integrating factor will be this. So this will be the integrating factor. So you need to have this in mind. Another way that we can do is we can swap q of x with p of y. So I swap it, but when I swap it now, my p is now the one what is at the last. So I divide by p. Q is here, I divide by q. So p is here, p is here. And this will be in terms of only y. And then now this will be the form of the integrating factor. So basically when you are doing it, you have to trial, like try this. If it doesn't work, then you try this. So that is basically what we just need to do. So let's go through the process, which is going to help us to learn basically what I'm trying to say, right? So let's do that. So first we need to check if it is exact, because okay, good. Since the question is going straight telling us that we should find the integrating factor, it means that it is not exact. So we can just go through by finding the integrating factor. So let's go through finding integrating factor. So we have x squared minus y squared plus 2xy dy over the x is equal to 0. Multiply through by the x squared minus y squared dx is equal to plus 2xy dy is equal to 0. Now, for us to find our integrating factor, we need the same process like the way we are doing for exactness. We need p of xy, which is equal to x squared minus y squared, and then we need q of xy, which is 2xy. Do you see that? So you see that when I differentiate p with respect to y, which is the same as py, this is equal to minus 2y. So this will be 0 and this will be that. Then when I differentiate q with respect to x, which is the same as qx, this is going to give us 2y. So you see that this and this are not the same. So it is not exact. So now what we just need to do is we need to find the integrating factor. So let's go by saying finding an integrating factor, let's say mu of x or mu of y. We don't know the one that we are going to get. The integrating factor can be in terms of x or y. So as I said, when we go further and we are dealing with ODE, you will see that we can even have integrating factor which is in terms of x and y, x squared plus y squared. We can have all those things, but in our form, in this level, we can think of integrating factor in terms of only x and integrating factor in terms of only y. So now let's find the integrating factor. So the first thing that we need to remember is we need to remember these two forms. One, p of x, no, p of y minus k of x divided by q, right? And then we have another one which is interchanging it by saying that k of x minus p of y divided by p. So this is what we just need to do to find out which one is going to give us in terms of only one function. So if this one gives us in terms of only one function, then we use this approach. If this one gives us only one function, then we use that one approach. So let's go through and see. So what is p of y? P of y is this. So I'm going to have minus 2y minus q of x is this, minus 2y divided by q of y. Oh, I said k of y divided by q. What is q? Q is this. So q is 2xy. Let's see what we are going to get from this guy. So here I can factor, or I can add. I have minus 4y divided by 2xy. Oh, nice. I can cancel y, and this is going to give us minus 2 divided by x. I can cancel 4 here, 2, and 2 here, 1. So this is what I'm going to get. And we see that this is in terms of only x. So this one works. But let's assume that we chose this one first. Let me go through this one. We chose this one first. And let's see if we are going to get it in terms of only one variable. So q of x is this. So I'm going to have 2x minus p of x is minus 2y divided by p. P is x squared, y squared from here. So let's do that. X squared minus y squared. Let's simplify. This is, oops, this one's supposed to be y. This is 4y divided by x squared minus y squared. Now we see that there is no way we can make sure that this is in terms of only y or x. So it means that if we pick this form first, then this is not going to work. So we don't need this guy. So now this is working for us. So this is what we just need. So look at what we've gotten. We are using the one that py comes first. So the one that py comes first is that we need to write it in this form, right? So what we can do is, after you've gotten something like this, then for us to get the integrating factor is very simple. It's very simple to recall. So this one is differentiate the integrating factor, which is x, because now the function is in terms of x. So the integrating factor should be in terms of x. So differentiate the integrating factor with respect to x, and this one should be equal to this with the integrating factor. So p of y minus q of x divided by q of divided by q with the integrating factor. So this is the form that you just need to learn. If it is y, this will just change to y. This will change to y, and this will swap x. No, I'll just swap it like with using the other one. So if it is y, that's what it's going to be. Good. Good. So now let's try and solve this. So the mu of x divided by dx is equal to this guy now is equal to this. So minus 2 divided by x mu. So we are back to separable. Let's separate this because we have the mu, right? And we have the x, and we have so let me just, we know that it's in terms of x, but let me just clean up the x so that we can just see that this is the mu. So we have the mu over the x as we saw it here, the mu over the x, and then we have 2 over x mu. So we need to group like terms in a way that we have them together. So this is going to be the mu, which is equal to minus 2 over x mu dx. So we need to take away the mu. So this implies that 1 over mu, the mu is equal to minus 2 over x dx. So we are back to separable. So what can we do? We can just integrate. So now we have 1 over mu, the mu, which is equal to minus 2 over x dx. So let's do the integration. 1 over mu, the mu, minus 2, 1 over x dx. So anytime I see 1 over something I'm integrating, I know that it's going to give us a ln function. So ln of mu is equal to minus 2 ln of, let's say, x. Yeah, something like that. Good. Now, when we are finding the integrating factor, mostly we don't concern about like the constant, right? But I can add plus constant here. Remember, I can add plus constant, subtract, and get constant the same thing. But basically, we can just ignore the constant, and we are okay with that, right? So we can just ignore the constant there. So this is the same as mu, which is equal to ln of x to the power minus 2. So I move this guy up here. I'm finding mu. So what do I need to do? I need to take the exponential function. So this is equal to e to the power x minus 2. And this is going to give us mu x to the power minus 2. And this is equal to 1 divided by x squared. So 1 divided by x squared is the integrating factor. So the integrating factor now is in terms of x. This is a lot of work. So now that you've gotten the integrating factor, so one thing about finding the integrating factor is when you are done, you don't need to go through the whole process again. What you can do is, now that you've gotten the integrating factor, you can start your solution from here, and then you are done, right? So now let's see what we can do. So we found out that for the function to be exact, we just need to multiply this function by the integrating factor and see if it is exact. So now let's go. We have the function to be x squared minus y squared dx plus, so I'm writing this, 2xy dy is equal to 0. So now that we've gotten the integrating factor, let's multiply through by the integrating factor. So we are going to have 1 divided by x squared minus y squared dx plus 1 divided by x squared 2xy dy is equal to 0. So now we can pick our new function. So now our new function now becomes mu of p of x. So you see that this one is p of xy, but this one is now, since we multiply by mu, we have mu of p of xy. So now this is going to be giving us x squared minus y squared divided by x squared. And then mu of k of xy is now going to be 2xy divided by x squared. This is the same as 2y divided by x. So now let's differentiate it. Now we need to differentiate this guy, mu of p, with respect to y. So let's do that. This one we are not going to use the quotient rule because the down here is constant. So when I differentiate x, I'll get 0. When I differentiate y, I'm going to have minus 2y divided by x squared. I hope you understand the differentiation. Now, you see, this is quotient rule, but this one is partially, right? So like I can write this one as 1 over x squared and then x squared minus y squared. Now this is a constant multiplying the function. So the constant, which is 1 over x squared, is here. When I differentiate this, I'll get 0. And when I differentiate this, I'm going to get 2 minus 2y. And then I'll multiply by this, and I have this one here. So pay attention to differentiation here. Then this also implies that this one I'm going to differentiate with respect to x. So I can write this one as 2y x to the power minus 1. Do you agree? Yes. Then we can write this one as partial of this with respect to q divided by x. So this one, I did it this way because now I'm differentiating with respect to x. So it is 2y, which is constant. So when I maintain 2y as a constant, then I need to differentiate this guy, which is going to give us minus x to the power minus 2. Simplify this and you're going to have minus 2y divided by x squared. So minus times this minus here comes down, and we will see that this is the same as that. So now we see that this was not the same as this, and we said it is not exact. But when we found the integrating factor, and then the integrating factor is correct, we see that now this is the same as that. So if your integrating factor is wrong, when you do this, this is not going to work out. So what can we say? Now we can say that since or thus the new, or thus, let me say thus, the integrating factor, okay, thus the differential equation is exact. It's exact now, right? Because this guy is the same as this guy. So it says that since partial of up with respect to y is the same as partial of mu q with respect to x. So now that is exact, we go through the same process. What's the process? We are saying that there is a function, let's say f of xy, such that when I differentiate this function f of xy with respect to x, now when I differentiate this one, this one is not equal to the p of xy again, because this is not exact. Now it's equal to this function. Where is it? Mu of p of xy. So that's what we just need to know. Now it's equal to mu of p of xy, right? And this is equal to x squared minus y squared divided by x squared. Let me call this guy equation 1. Then f of y with respect to x now is equal to mu of q of xy, which is equal to, what is equal to? Is equal to what is it? Okay, it's equal to this. So this is equal to 2y over x, and I call this one equation 2. Good. Here is where the magic happens. You see, anytime we have something like this, we need to integrate. So we can integrate this with respect to x, or integrate this with respect to y. So the question is, you need to pick the one you think, that is the idea, that you think you can integrate first. For me, I can integrate this one first or this one first. Any of them holds. It's just kind of very simple, right? So I can start from equation 1. Right? Good. So I'm going to start from equation 1 and do the integration. You can start from equation 2 and do it too as well. So let me add another page to it. So from equation 1, we want to integrate equation 1 with respect to x. So we want to integrate this with respect to x. So we are going to have integrate f of x y with respect to x, and then we are integrating x squared minus y squared divided by x squared dx, right? I hope the same function. Okay. So this is the function that we want to integrate. So when I integrate this, because the function is differentiated, I'm just going to have f of x, y as usual. And then for me to integrate this, I need to do some small manipulation here. So I can write this one as x squared divided by x squared minus y squared divided by x squared. And then this is the same as 1 minus y squared, or let me say x to the power minus 2y squared, or the x. So that's why I said always pick the one that you think you can integrate fast. So this is 1. Now when I move this one up, become minus 2. So now I can now do the integration. When I integrate a constant with respect to x, I get just the constant times x. And then minus, when I integrate this, I'm going to have x to the power minus 2 plus 1 divided by minus 2 plus 1 times my y squared, because y is a constant multiplying the function. And don't forget to add your this with respect to y, because now the function is in terms of xy, so we add this one to it. Now let's simplify, and we are going to have x minus x to the power minus 1 divided by minus 1 y squared plus phi of y, and this is going to give us x plus 1 divided by x y squared plus that. I have gotten it. So this minus here become positive, and I have y squared divided by this is to the power minus 1, so become division. So now this is f of x y, which we call this one a special function, because basically this is the general solution. So we just need to go and look for this guy. So we've made use of equation 1, so we need to make use of equation 2. So what do we need to do? Because we want to use equation 2, then we need to differentiate equation star with respect to y. So let's do that. So now let's differentiate this with respect to y. So fy of x will be equal to, this one will be 0, because we are just differentiating with respect to y. When I differentiate this with respect to y, what am I going to get? I'm going to have 2y divided by x, because the x is constant, so I just differentiate the top, plus now I differentiate this and I get y prime of this. Let me call this one equation 3. So now we see that equation 3 and equation 2 are the same, because we have this one here and then we have this one here. So we say equate equation 3 and equation 2. So what is equation 3? Equation 3 is 2y divided by x plus phi prime of y, which is equal to equation 2. What is equation 2? Equation 2 is this, 2y over x. So you are going to get 2y over x. Now when I move this one to this side, it becomes minus, so it will be 0. So I'm going to have phi prime of y to be equal to 0. So now from my equation star, I need phi of y. So I need to integrate this. So integrate phi prime of y, which is equal to integration of 0 with respect to y. And phi of y is basically equal to constant, because when I differentiate a constant, I need to get 0. Good. So now let me call this one equation 4 and say put equation 4 into our special equation, what is equation star. So what are we going to get in there? We are going to have f of x y to be equal to x plus y squared over x plus this, and this is c, so plus c. Now let's call this one c1, and we know that if this one is c1, then what do we need to do? We need to say that this is equal to c2. So let's assume, let me just shift these people to the side small, and then just see that now from here we let f of xy to be equal to c2, so c2 will be equal to x plus y squared divided by x plus c1, x plus y squared over x plus c1 minus c2 will be equal to 0. So the general solution will be y squared over x plus c is equal to 0. And this is the general solution. Do we have initial condition given? No, there is no initial condition given. So this is the general solution. Let's take another one. Let's take another one. Let's take another one. Then I'll give you a trial one to do. So this one too, the question is open. So I'll show you the trick that we need to learn here. Since it's open like this, then we know that we are dealing with integrating factor. So definitely we need to find integrating factor. But let's start from whatever we've learned. So whatever we've learned is now we need to check if the function is linear. How do we check linear? Linear is when we have dy over dx plus gen of x y is equal to h of x. So we ask ourselves, can I write this function in this form? No, this is not possible, right? Because basically, if I do this, this is not going to work. It's not going to work. So linear is out of the equation. Then I need to think about separable. This is not separable. So because you can even see that dx is going with a function with y and dy is going a function with x. So separable is not working. So the next thing that we need to think about is we need to think about homogeneous. Is it possible for homogeneous? Now when I multiply this, I'm going to have x squared minus 2xy. So the degree here is 2, the degree here is 2. Okay. The degree here is 2, the degree here is 2, but this is constant. So because of this constant, we cannot use homogeneous because degree here is 2, degree here is 2. Because this one is 1, you cannot factor lambda out. So we don't have any choice but think of exact differential equation. So when we start exact differential equation, that is when we will know whether the differential equation is exact or not. Then we can think about looking for the integrating factor. So now let's think about exact differential equation. So now first we pick our p of x because the function is already done for us. So p of x y dx plus k of x y dy is equal to 0. So this is x squared plus y squared plus 1, and k of x y is equal to x minus 2y, and this is the same as x squared minus 2xy. So let's find for partial of p with respect to y. This is going to give us 2y. Let's find for partial of k with respect to x. This is going to give us 2x minus 2y. So indeed, this is not the same as this. So we are going to conclude that the differential equation is not exact. So thus, the differential equation is not exact since partial of p with respect to y is not the same as partial of k with respect to x. So now it means that for us to solve, since the question says that we need to solve, then we need to think of finding integrating factor. So let's go through by finding integrating factor. So finding an integrating factor. So remember what we just need to do. We need to pick p of y, which is minus k of x divided by this, right? That's one of them. So I can write it fully. This divided by, this one is going with x. So this with x times this. So this is one of them. Or we can pick mu with respect to y, and this will be k of x minus p of y divided by p, and then mu. So one of them should work. But for one of them to work, we need to pick the one in the parentheses and work with them and see which one is going to work. Now don't forget, this is the same as p of y, and this is the same as k of x. So let's do that. Let's pick the first one here. So let's work with p minus this divided by q. What is p of y? That is 2y minus what is q of x? That is what is here. So we are going to have 2x minus 2y. Then divided by q. Q is this. So q is x squared, or we can even use x minus 2y. Right. So that is q here, q of x, p of x. So let's try and simplify and see if we can leave it in terms of only x. If not, then that one is not an option. So this will be 2y minus 2x plus 2y divided by x minus 2y. So let's see. This is the same as minus 2x plus 4y divided by x minus 2y. I think this one we can do something about it. Now here I can factor minus 2 out. So when I factor minus 2 out, this one is going to be x and this one is going to be minus 2y. Is that true? This time this will be this, and then minus 2 times this will be that. Good, that's true. So this will be x minus 2y. Nice. Oh, nice. So now we are going to have this one to be minus 2 divided by x. Good. So without even doing the other side, we know that this is going to work. So we don't need to go through this. So we can just clean this one out, or we can try and see if this is going to work. So let's see. If one work, the other one is definitely going to work. But let's try it and see. Qx minus py divided by p is equal to, so qx is 2x minus 2y minus py is that. So this is qx minus py, then divided by p is x squared plus 1. So you can even see that there's no way we can cancel some things out here, because this is 2x minus 4y divided by x squared plus y squared plus 1. There's no way, even if you do factor here, there's no way, because of the constant here, we cannot factor. So this is not going to work. Good. So always one work, the other one will not work. So now this is what you've gotten. So now since this guy here is equal to this, I can place it here. So I'm going to have from here, I'm going to have something like this. The mu over dx, which is equal to minus 2x mu. So the same process again. I think we've done something like this. I think the other one, the integrating factor, was also the same. So let's group like terms. The mu is equal to minus 2 over x mu dx. Then we will divide through by 1 over mu, which is equal to minus 2 over x. I think we've done something like this. So this is minus 2 out, 1 over x dx. Oh, okay, I think so. So let's do the integration. This is going to be this, which is equal to minus 2 ln of x. So as I said, we are finding integrating factor, so we don't want to add constant, because even though when you are done, we just ignore the constant, or may say that the constant is 1. So we don't need to add the constant. So what we need to do here, we need to find the exponential function, right, on both sides. So ln of mu of this is equal to e to the power minus 2 ln of x. And that's what we are going to get. So we are going to get mu is equal to e to the power ln of x minus 2 from here, because we need to move the minus 2 up. And this is going to give us mu of x, which is equal to x to the power minus 2, which is the same as 1 over x squared. So this is the integrating factor now. So now that we've gotten the integrating factor, we need to multiply the integrating factor by or through this before now we can check it out. So now we have x squared plus y squared plus 1 dx plus x minus 2y dy is equal to 0. So now let's multiply through by the integrating factor. We are going to have 1 over x squared y squared plus 1 dx plus 1 over x squared times x minus 2y dy. So now we pick our new functions. So now we are going to have mu of p of x, y, because now we are dealing with integrating factor, which is 1 over x squared times x squared plus y squared plus 1, and this is the same as when I multiply through by the 1 over x squared, I'm going to have 1 plus y squared over x squared plus 1 over x squared. Then I need this guy, mu of q of x, y. This is 1 over x squared times x squared, no, x minus 2y. And this is the same as when I cancel it out, I'm going to have 1 over x minus y, right? So one of them cancel. And when I multiply it through, I'll have 1 minus 2y over x. So what we need to differentiate them. So I pick the partial of up with respect to y. So let's differentiate this with respect to y. I differentiate this, I'll get 0. Differentiate this, I'll get 0. Now differentiate this. Now 1 over x squared is constant because I'm differentiating with respect to y. So I'm going to have 2y divided by x squared, which is very nice. Now let's check with this one too. Mu of q with respect to x. Now differentiating this with respect to x. Now we can write this one as 1 minus 2y x to the power minus 1. So when I differentiate 1, I'll get 0. Now I'm going to have minus 2y, then differentiate minus 1 to the power x to the power minus 1. So minus 1x that. And this is going to be minus minus will be positive. So I'm going to have 2y x to the power minus 2. And this is the same as 2y divided by x squared, which is the same as that. So this is true. Now it indeed shows that 1 over x squared is the integrating factor, and this helps us to show that now the integration, the differential equation becomes exact, and we can use the exact process to solve the function. So let's do this one. I'll give you one example to try. So let's see how we can get this. Now we are saying that the differential equation is exact, or whenever we find the integrating factor, we can say that the integrating the differential equation becomes so that exact, then partial of mu p with respect to y is the same as partial of this with respect to x, right? So if that's the true, if that's the case, then there exists a function f of x y such that when I differentiate the function with respect to x, I get mu of p. Mu of p is, what's mu of p? Is this. So 1 plus y squared over x squared, and then 1 over x squared. Then when I differentiate it with respect to y, that's mu q, and that one is 1 minus 2y over x. So let me call this guy equation 1, equation 2. So as I said, always choose the one you can integrate fast. So which one can I integrate? Okay, the way the function is, I think I can integrate all of them very fast. So the first one I started from 1. This one too, let me start from 2. So let me get to another sheet. Let me just bring another sheet. So I'm starting from equation 2. So from equation 2, what was the equation there? So from equation 2, which is fy of xy is equal to 1 minus 2y over x. So I need to integrate that with respect to y. Integrate this with respect to y. So this is going to give us f of xy. So this differentiated, integrate, the function comes. And then I can write this one as this one. Let me just write it for you to see. This is the same as 1 minus 2y, or let me say 1 minus 2 over x times y dy. So that now when I integrate a constant, I just multiply by y. So this will be y minus, now we are integrating y and this is a constant, multiplying it. So this will be 2 over x, y squared over 2, right? Plus now a function in terms of x, because we are integrating with respect to y, and this is two functions. So now I'm going to have y, these two will cancel these two, so I'm going to have y squared divided by x plus 5 of this. And this is the special function that we are looking for. That is the star f of x, y. So we've made use of equation 2. We need to make use of equation 1. So what do we need to do? We need to differentiate equation star with respect to x. So let's do that. Differentiating this with respect to x. Differentiate y partially, get 0. Now differentiating this here can be written as minus y x to the power minus 1, right? Good. So this one is the same as when I differentiate, this one will be 0. So this one is going to be minus y squared. Then when I differentiate minus x to the power minus 1, I have minus x minus 2 plus phi prime of x. And let me simplify this one some more before I call it equation 4 or 3. This is going to be minus minus will be positive, so I'm going to have y squared divided by x plus phi prime of x. Let me call this equation, let's say equation 3. So now you see that now equation 3 and equation 1 are the same. F is with respect to x, and then f is with respect to x. So let's equate. So you see, we go through the same process of doing everything, but the only things that changes is the differentiation and then the integrating factors that you are going to find. They are the things that is going to just change. So this is going to be y squared over x squared plus phi prime of x, which is equal to equation, oh, that one should be equation 1. So this one should be equation 1. So this is 1 minus y squared over x squared plus, let me just check it again. Oh, it's supposed to be plus 1 over x squared. So when I move this one to this side, it will cancel this. This will cancel that. So I'm going to have this prime is equal to 1 plus, 1 over x squared can be written as x to the power minus 2. Then from the equation start, we need phi of x. So we need to integrate here. Integrate this with respect to x. Integrate this with respect to x. So what do we get? This will be this, which will be equal to, when I integrate 1 with respect to x, I multiply by x. So this one will be x plus minus 1 divided by minus 1. So add plus 1, then minus 2 plus 1. Then this is in terms of only one function, so I add c. So I'm going to have phi of x to be equal to x minus 1 over x plus c. Let me call this guy equation 4. So the special thing to do here is put equation 4 into our special equation, which is equation star. So what is equation star? Equation star is this guy. So let's just put it inside and see what we are going to get. So we are going to have f of xy to be equal to y minus y squared over x, yes, plus this, and this is this. plus x minus 1 over x plus, okay, let me make this one c1, c1. So what we just need to do is we just need to just set our let f of x y to be equal to c2. So we are going to have c2 to be equal to y minus y squared divided by x plus x minus 1 over x plus c1, and this is y minus y squared divided by x plus x minus 1 over x plus c1 minus c2 is equal to 0, is equal to 0. Good. So y minus y over 2 plus x minus 1 over x plus c is equal to 0. So this is the general solution. There is no initial condition for us to find the particular solution. So this is the process of going through the idea of what? Finding integrating factor and using the integrating factor to find the general solution. Right. Now try this. First, show that 1 over x squared is the integrating factor of this function. When you are done, then you just try to find the integrating factor and then find the general solution for this. Now, what is new? Now, in the next video, we are going to talk about second order differential equation. So all the things that we've done is first order differential equation, because you will see that, for example, this is like y prime. So it's like dy over dx. Now, in the next video, we're going to talk about second order differential equation, which goes with y prime prime, which is dy squared over dx squared, right? Since the order is increasing, we can also have an equation which involves just the first order, but we are going to have it to be second order as well. So in the next video, we are going to talk about second order differential equation, and I hope you are going to enjoy it. Make sure you solve it and you leave your solution in the comment section. See you in the next video.